Hello there, and welcome to the Sleepy Space Channel. Tonight, a strange fact about the body and the universe. The room around you is still, the bed is steady, and yet, at this moment, you are being carried through space at a speed no human nerve can register. The conventional figure is more than 800,000 miles per hour toward the constellation Leo. A new measurement, drawn from a continent-wide radio survey of distant galaxies, suggests that the true number may be more than 3 times larger. The dipole came in 3.7 times stronger than predicted. If taken at face value, it would mean the Earth is sailing through the cosmic frame at over 2 million miles per hour, in complete silence, while the body lies still. Tonight we walk through the layered motions that carry you, and the new measurement that has reopened the question. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is something you need to carry. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. Part 1. The question beneath the motion. There is a quiet contradiction at the heart of where we live. The Earth feels still. The room is steady. The bed does not shift. The lamp does not sway. Outside the window, the trees stand where they stood yesterday, and the line of the horizon holds the same gentle curve it has always held. Nothing about the experience of being on the surface of this planet feels like motion. And yet, the surface of this planet is one of the fastest moving things in the known universe. Not just the planet, but the body resting on it. Not just the body, but the air around the body. Not just the air, but the room, the building, the city, the whole continent. Every part of the immediate world is, at this moment, being carried at speeds the body has no nerve to register and no language to describe. The Earth is moving. The Sun is moving. The galaxy that holds the Sun is moving. The small cluster of galaxies that holds our galaxy is moving. And the larger structure that holds our cluster is itself moving, drawn slowly through the cosmic web by a gravitational pull that astronomers have only recently begun to map. Beneath the still surface of an ordinary night, there is a stack of motions so large that no single number describes them all. This video is about that stack. It is about the layered motions that carry the Earth through space, the speeds and directions of each layer, the way they fold together into a single combined motion, and a recent measurement that has quietly suggested the combined motion may be far greater than anyone realized. The question the video asks is simple at the surface. How fast is our solar system moving through space? But the question has more than one answer, because the solar system is not moving in only one frame. It moves relative to the nearby stars. It moves relative to the average circular orbit those stars trace around the galactic center. It moves relative to the galactic disk as a whole. It moves relative to our small cluster of nearby galaxies. It moves relative to the larger network of galaxies around our cluster. And it moves relative to the oldest light in the universe, the cosmic microwave background, the closest thing the universe has to a universal reference frame. Each of those motions is real. Each has been measured. Each carries a different number in a different direction against a different reference. And the total motion of the Earth, when all of those layers are added together, comes out to a speed that would have astonished any earlier astronomer who first sat with the question. Yet that total has just been challenged. A new study, using a vast network of radio telescopes across Europe, has counted the distant radio galaxies of the sky in every direction. The pattern of their distribution has produced a measurement of our motion that is more than 3 times larger than the standard model of cosmology predicts. The result has been confirmed at the conventional thresholds of statistical significance, and it has reopened a question that astronomers had considered, for the most part, settled. What follows is a slow walk through the layers of motion that make up the answer. We will begin with the smallest scale, the orbit of the Earth around the Sun, and work outward, one layer at a time, until we arrive at the scale of the radio galaxy measurement and the strange threefold discrepancy at the largest known reference frame. We will not move quickly. The motions we are describing are immense, but the pace of the description will be slow, because the audience is here to drift, not to race. The body resting on the surface of the Earth tonight is being carried by the largest current the universe makes available to anything. It is one of the strangest gifts of physics that none of that current can be felt. The room is still. The breath is slow. The frame is doing all of the carrying. The mystery here is not what is moving. The mystery is the gap between what is moving and what can be felt. Every layer of motion in this video is established. Every layer has been measured. Every layer has been independently confirmed by multiple methods. The numbers in this video are not speculative. They are textbook figures refined over decades that represent the best current understanding of how the Earth moves through the universe. The only number under fresh scrutiny is the largest one, and even that is a refinement rather than an overturning. The Earth was already known to be moving very fast. The new measurement only suggests it may be moving even faster than that. What is striking, in the calm view, is not the individual numbers. It is the cumulative picture. The body, lying on a small rocky planet, on the surface of a small moving star, in a small drifting neighborhood, in a small orbiting galaxy, in a small flowing cluster, in a small cosmic region drawn slowly toward a deeper cosmic well, is, in this very moment, sailing through the universe at a speed no human being has ever felt. The body is participating in every one of those motions, without participating in any of them in any noticeable way. The frame is doing all of it. There is also something soft in the structure of the question itself. The question begins simply as a single number and unfolds into a layered answer because the universe is itself layered. There is no single coordinate frame in which all motion is measured. There are many frames, each one nested inside the next, each one with its own conventions, its own zero point, its own preferred direction. To answer the question of speed, the universe quietly insists on first being told the frame. And once the frame is named, the answer falls out in numbers that grow larger and larger as the frame grows wider. This will be a slow tour through those frames. From the smallest scale of the Earth orbiting the Sun, outward to the Sun moving among nearby stars, outward to the Sun moving around the center of the galaxy, outward to the galaxy moving inside the local group of galaxies, outward to the local group flowing through the larger supercluster, and finally, outward to the largest measured frame of all, the cosmic microwave background. Each frame is a real frame. Each frame has been measured. Each frame produces a different number for the same question. By the end of the tour, we will arrive at the new measurement and at the strange and quietly extraordinary possibility that the largest of those numbers, the speed at the largest scale, may be more than 3 times larger than astronomers thought. Whether or not the result holds up, the path to it is a calm path, and the layered motions underneath are settled facts. The Earth is moving, faster than the body can ever feel, in every frame that has ever been used to measure it. The night is steady. The room is quiet. The current is doing the carrying. Part 2. The Earth around the Sun. The first layer of motion is the most familiar one. The Earth orbits the Sun. It traces a path that is very nearly a circle, although close attention reveals it to be a gently elongated ellipse with the Sun slightly off-center. The orbit takes 1 year to complete. The distance covered in that year is enormous. The Earth lies on average about 93 million miles from the Sun. That distance is large enough to require its own name in astronomy, the astronomical unit. It is the basic ruler of the inner solar system. When astronomers want to describe the distance from the Sun to Mars or from the Sun to Jupiter, they typically express it in astronomical units, because the actual figures in miles or kilometers are too cumbersome to hold in mind. The full path the Earth follows in a year is the perimeter of that elliptical orbit. To complete the path in a single year, the Earth has to move along it at a steady pace of roughly 30 kilometers per second, which is about 67,000 miles per hour. That is the speed at which the planet, with everything on it, is sailing through space along its orbital track at this moment. The number is difficult to feel. 30 kilometers per second is many times the speed of a commercial airliner, many times the speed of a rifle bullet, many times the speed of a meteor entering the upper atmosphere. It is faster than any sustained motion a human-built vehicle has ever held, and yet the body experiences none of it. The ground is steady. The sky is calm. The lamp does not move. There is no sensation of being on a vehicle traveling at 67,000 miles per hour through the dark. The reason for that absence of sensation lies in a basic principle of physics. The body cannot feel motion at a constant velocity. It can feel only changes in velocity, the small pushes and pulls of acceleration. The Earth's orbital motion is, for all practical purposes, constant in magnitude. Its direction is slowly changing as the planet curves around the Sun, but the change is so gradual and the centripetal acceleration so small compared to gravity that the body never registers it. The whole motion is invisible from inside. There is a small variation in the orbital speed across the year. The Earth's orbit is not a perfect circle, and the planet moves slightly faster when it is closer to the Sun and slightly slower when it is farther away. Near the closest point of the orbit, called perihelion, the speed climbs to about 30.3 kilometers per second. Near the farthest point, called aphelion, it drops to about 29.3. The difference is small, but it follows the same pattern that governs every orbit in the solar system. A body sweeps out equal areas of its orbit in equal times. When the radius is shorter, the body must travel faster to keep the swept area equal. When the radius is longer, it travels slower. The orbit pulses across the year, faster and slower, but the average remains near 30 kilometers per second. That orbital motion is one of the few motions of the Earth that can be measured directly from the planet's surface without leaving it. The Earth's annual swing across one side of the Sun and back produces a small periodic shift in the apparent positions of nearby stars. Across the year, the closest stars appear to trace tiny ellipses against the more distant background. That motion is called stellar parallax, and it was the first direct observational proof that the Earth orbits the Sun. It is the universe's way of confirming what the body cannot feel. Beneath the orbital motion, the Earth carries several smaller motions. It rotates on its axis once a day, sweeping a point on the equator around at 1,000 miles per hour. It wobbles slowly on that axis across a cycle of about 26,000 years, in the motion called the precession of the equinoxes. It nods very slightly on a shorter cycle. It drifts away from the Moon as the Moon gradually recedes. Each of these motions is real. None of them are felt. And all of them are folded into the orbit, and the orbit is folded into the Sun's much larger motion through the galaxy, which is the next layer outward. It is worth pausing on the geometry of the orbit itself before leaving it behind. The plane of the Earth's orbit, called the ecliptic plane, is the reference plane for the entire solar system. The other planets all orbit roughly in the same plane, with small tilts. The Sun's equator lies close to the same plane, with its own small tilt of about 7 degrees. The planets themselves rotate roughly in the same direction as their orbital motion, with the prominent exceptions of Venus and Uranus, which have their own anomalies. The shared plane is a relic of the rotating disk of gas and dust from which the solar system formed 4.5 billion years ago. Every planet, every moon, every asteroid still orbiting today carries forward the memory of that initial disk in its motion. The orbital path of the Earth in that shared plane is a path roughly 584 million miles long, traced out once a year. That is the perimeter of the orbit. The full path is folded around the Sun in such a way that one full circuit takes precisely 1 year, by definition. The year, in a deep sense, is the time it takes the Earth to walk that path. The seasons are the slow result of the Earth's tilt against that path, with the axis pointing toward the same fixed direction in space throughout the year, so that different parts of the planet are tipped toward the Sun at different points along the orbit. There is one more layer worth naming. The Earth and Moon together form a small system that orbits a common center of mass, called the barycenter. The barycenter lies inside the body of the Earth, but not at the geometric center, because the Moon is large enough to displace the balance point. As the Moon orbits, the Earth wobbles slightly around the barycenter, and the path of the Earth around the Sun is not perfectly smooth, but a small monthly waver. From the outside, the Earth and Moon together trace a small dance around the Sun, with the barycenter following the smooth orbital track and the Earth and Moon swinging around each other along the way. That dance is real, but its scale is so small compared to the orbital motion as a whole that it is invisible at the level of detail we are working in. The 30 kilometers per second is the dominant motion, with the monthly dance superimposed on it as a fine tracery. The orbital motion of the Earth around the Sun is, in the long picture, the smallest layer the body participates in. Every layer beyond it is larger by a factor of 10 or more. But it is also the most familiar layer, the one most immediately visible in the rhythm of the year, the changing position of the Sun in the sky, the slow march of the constellations from one season to the next. The orbit is the easiest motion to name and to feel as a pattern. Once one steps outward to the Sun's motion through the galaxy, the patterns become slower, the timescales longer, and the motions much harder to perceive, even in principle. Part 3. The Sun through the local neighborhood. The Sun is not at rest among the stars around it. It is moving through them, slowly, in a direction that has been precisely measured. To describe that motion, astronomers compare the Sun's velocity to an idealized reference frame called the local standard of rest. The local standard of rest is the frame that would correspond to a perfect circular orbit around the galactic center at the Sun's current distance. It is a useful abstraction. By comparing any star's velocity to that idealized circular orbit, astronomers can describe the star's peculiar motion, separate from the much larger circular motion shared by every star in the disk. The Sun's peculiar velocity, measured against the local standard of rest, is about 13 kilometers per second. It is much smaller than the orbital speed of the galaxy as a whole, but it is enough to carry the Sun across the distance to a nearby star in a few 100,000 years. The direction of that motion has a name. It is called the solar apex, The apex is the point on the sky toward which the Sun is currently drifting, relative to the nearby stars. It sits in the constellation Hercules, not far from the bright star Vega, roughly between the 4 stars that mark the keystone of Hercules. From a vantage point above the galaxy, the Sun is drifting slowly in that direction, threading through a small fraction of the local stellar neighborhood every few 100,000 years. The opposite point on the sky, the direction the Sun is moving away from, is called the antipex. It sits in the constellation Columba, low in the southern sky from most northern latitudes. The line drawn between Hercules and Columba is the line along which the Sun is currently moving through its local stellar bath. There is something quietly remarkable about that fact. Every clear summer night, Hercules rises in the east. And every night, the Sun, with the Earth on its back, is moving slowly toward that exact patch of sky at about 13 kilometers per second. Hercules is not the destination of the Sun. It is simply the direction the Sun is going at this moment in its slow drift through the local neighborhood. In a few tens of millions of years, the local stars will have rearranged themselves enough that the apex direction will shift to a different constellation. The apex is a present tense address. It is not a permanent one. The reason the Sun has a peculiar velocity at all is that the galactic disk is not perfectly smooth. If every star in the disk were on a perfect circular orbit at the local rotation speed, every star would share the same velocity, and the Sun would have no peculiar motion to measure. But stars are born in clusters from collapsing clouds of gas, and the clouds carry their own small motions. Stars are then perturbed by passing molecular clouds, by close stellar encounters, by encounters with the spiral arms, by the slow gravitational stir of the galactic bar. All of these effects add small randomized motions on top of the average circular orbit. The result is that every star in the disk has its own slightly idiosyncratic path. Some orbit a little faster than the local average. Some orbit a little slower. Some climb slightly above the plane of the disk and back down. Some have orbits that are slightly more elliptical than circular. The Sun's peculiar velocity is the Sun's particular share of that scatter. The Sun drifts inward and slightly upward through the disk at 13 kilometers per second, on top of the much faster motion that the whole disk is participating in. The Sun, in this sense, is an ordinary star with an ordinary peculiar velocity. The numbers are unremarkable. The direction is unremarkable. The Sun's place in the local neighborhood is unremarkable in every way except one. It is the only place in that neighborhood from which the question of its own motion is being asked. The stars within a few hundred light-years of the Sun share, on average, the same orbital motion around the galactic center, with their own small peculiar velocities layered on top. The Sun's peculiar velocity is small enough that it will spend tens of millions of years among more or less the same local stars before the slow drift carries it into a different stellar bath altogether. The local neighborhood is, on human timescales, a stable companion. On galactic timescales, it is a passing crowd. There is also a structure beyond the local neighborhood that is worth naming. The Sun and its neighbors lie inside a larger region of low-density gas called the local bubble, a roughly spherical region about 300 light-years across that has been blown clear by ancient supernovae that exploded in this part of the galaxy over the past several million years. Inside the local bubble, the interstellar medium is much thinner than the galactic average, and the Sun and its planets move through this thin gas as they drift through the local stellar bath. The local bubble is itself moving, of course, along with the rest of the disk, but on the scale of the Sun's peculiar motion through the local stars, the bubble is essentially stationary background. Just inside the local bubble lies a smaller cloud called the local interstellar cloud, which the Sun is currently passing through. The cloud is a slightly denser concentration of warm gas, a few tens of light years across, drifting through the wider local bubble at its own peculiar velocity. The Sun entered the cloud somewhere in the last few tens of thousands of years, and will exit it on the same timescale, having spent a moment of galactic time embedded in a particular wisp of interstellar gas. The local interstellar cloud is one of many small structures in the wider bubble. The boundary between the cloud and the surrounding bubble is gradual, not sharp. There is no membrane to cross. The Sun is simply moving through gas of slightly different temperature and density, and the change is registered, when it is registered at all, only by the most sensitive instruments, measuring the inflow of interstellar atoms into the solar system. The picture of the Sun moving through its local neighborhood is, then, a picture of layered structures. The nearest stars form one frame. The local interstellar cloud forms another. The local bubble forms another. The wider galactic disk forms another. Each is moving in its own way, with its own peculiar velocities. The Sun threads through all of them at the same time, carrying the planets carrying the moons carrying whatever finely tuned biology or geology happens to be developing on their surfaces. The 13 kilometers per second drift of the Sun toward Hercules is, in this layered picture, a present tense address among many present tense addresses. The Sun is passing this way through this part of the disk. It will not always be here. It has not always been here. The slow drift is one of the few motions of the Sun that changes appreciably on the timescale of stellar evolution. A few 100 million years from now, the Sun will be in a different neighborhood, with different nearby stars, drifting in a different direction relative to that new neighborhood. The motion is real, but its specific value is local in time, just as it is local in space. Part 4. The Sun around the galaxy. Beneath the slow drift through the local stars lies a much faster motion. The Sun orbits the center of the Milky Way. The orbit is enormous, the orbital speed is large, and the period is long. To complete a single trip around the galactic center, the Sun takes roughly 225 to 250 million years. That interval is called a galactic year. The Sun lies about 26,000 light-years from the center of the galaxy. It moves around that center at a speed of roughly 220 kilometers per second, which is about 500,000 miles per hour. That speed is much larger than the orbital speed of the Earth around the Sun, and much larger than the Sun's peculiar velocity through the local neighborhood. It is the dominant motion the solar system shares with the rest of the disk. To compare the scales, the Earth orbits the Sun at 30 kilometers per second. The Sun orbits the galactic center at more than 7 times that speed. And the Sun's peculiar velocity through the local stars is about a 20th of the orbital speed around the galaxy. The orbital motion swamps the local drift by a wide margin, and is itself the dominant carrier of the solar system through the larger structure of the Milky Way. The Sun and its planets are estimated to be about 4.5 billion years old. At a galactic year of roughly 225 million years, that means the solar system has made about 20 complete trips around the galactic center since it formed. 20 galactic years is the total tenure of the solar system in the galaxy. When the Sun first lit up in its birth cloud, the local neighborhood was a different one. The constellations on the sky from Earth, if Earth had existed yet, would have been entirely unrecognizable because the Sun was on the other side of the galaxy from where it is now, surrounded by an entirely different set of stars. The Sun has been a steady traveler on a steady track for those 20 galactic years. The orbit is not perfectly circular. It is slightly elliptical, and the Sun does bob slightly above and below the plane of the galactic disk over time, drifting through the disk in a slow vertical wave that takes tens of millions of years to complete a full oscillation. But the broad pattern is a long, looping circle around the galactic center, carrying with it the Earth, the Moon, the planets, the asteroids, the comets, and every piece of debris bound to the Sun by gravity. The direction of the galactic orbit at this moment is roughly toward the constellation Cygnus. Cygnus is a long, bright cross of stars near the brightest river of the Milky Way overhead in the northern summer sky. And the Sun, every night, is moving roughly toward that constellation at 500,000 miles per hour, threading along the disk with the rest of the local stars. That direction is not the same as the solar apex. The apex points toward Hercules and represents the Sun's slow, peculiar drift through the local neighborhood at 13 kilometers per second. The galactic orbital direction is a separate, much faster motion toward Cygnus, carrying the entire neighborhood with the Sun. The two motions are layered. The Sun drifts toward Hercules at 13 kilometers per second, within a neighborhood that is itself being carried towards Cygnus at 220 kilometers per second. The Milky Way's rotation has a famous shape when plotted as a curve. Out to a few thousand light-years from the center, the orbital speed climbs rapidly with distance from the center. Beyond that, however, the curve does something strange. It flattens out and stays roughly constant at around 200 to 240 kilometers per second across vast ranges of distance, all the way out to the visible edge of the disk. The outer stars are not orbiting more slowly than the inner ones, as a simple gravitational model based on the visible matter alone would predict. They are orbiting at almost the same speed. That flat rotation curve was one of the earliest observations that pointed toward the existence of dark matter. To hold the outer stars at such high orbital speeds, the galaxy must contain much more mass than its luminous stars and gas alone account for. The extra mass is distributed in a roughly spherical halo around the visible disk, invisible to telescopes but felt through its gravity. The dark matter halo is what allows the outer disk to rotate at the speed it does. The Sun, at 26,000 light-years from the center, is well inside the flat rotation region. Its orbital speed of 220 kilometers per second is the local circular orbital speed at that radius. It is the speed that any star at that radius on a near-circular orbit would carry. The Sun simply rides the standard rotation curve of its part of the galaxy, along with several 100 billion other stars. The structure of the galaxy through which the Sun moves is itself worth describing for a moment. The Milky Way is a barred spiral galaxy with a central bulge of older stars, a long bar across the center, and several spiral arms winding outward. The arms are not solid structures of stars. They are slow-moving density waves through the disk, regions of slightly higher density of gas, dust, and young stars. As the Sun orbits the galactic center, it passes through the arms periodically, on a timescale of roughly 100 million years between crossings. Each crossing exposes the solar system to a slightly denser local environment, with more nearby star formation, more potential supernovae, and more interstellar gas to plow through. The Sun is currently between two of the major spiral arms, in a smaller structure called the Orion Spur or Orion Arm, sometimes also called the Local Arm. The Orion Arm is a minor branch of the larger Sagittarius Arm, named for the constellation that lies in its direction. On the other side of the Sun in the direction away from the galactic center, lies the Perseus arm. The Sun is in a relatively quiet region between these larger structures, neither inside a major arm nor in a deep gap between them. The orbit of the Sun around the galaxy takes it through the cycle of arm crossings and interarm regions over the course of each galactic year. There has been speculation, never confirmed at the level of solid science, that some patterns in the Earth's fossil record might correlate with these arm crossings, perhaps through changes in the cosmic ray flux or the rate of nearby supernovae. The evidence is suggestive, but not decisive. What is certain is that the Sun has crossed several spiral arms in the course of its lifetime in the galaxy, and the planets and moons of the solar system have moved through environments of varying density and varying radiation along the way. The vertical motion of the Sun within the galactic disk is also worth naming. The disk is not a perfectly thin sheet. It has a vertical thickness of a few hundred light-years, with stars and gas distributed in a layered pattern that thins out away from the central plane. The Sun, like most disk stars, oscillates slightly above and below the plane on a long vertical period of roughly 70 million years. The amplitude of the oscillation is modest, perhaps a few hundred light-years, but it is real. At this moment, the Sun is slightly above the plane of the disk and slowly moving back toward it. Over the course of a galactic year, the Sun would complete roughly 3 full vertical oscillations. The combined picture is a Sun that spirals slowly through a structured disk, threading between density wave arms, oscillating gently above and below the central plane, drifting at its own peculiar velocity through the local stellar bath, all while orbiting the galactic center at 220 kilometers per second. The motion is layered. The frame of the Sun's orbit is itself a frame within a frame within a frame. Part 5. The Milky Way through the local group. The Milky Way is not isolated. It belongs to a small cluster of galaxies called the local group, gravitationally bound together by mutual attraction. The local group contains 2 large spiral galaxies, the Milky Way and the Andromeda Galaxy, along with about 100 smaller galaxies, most of them dwarf companions of the 2 giants. The whole cluster spans a region about 10 million light-years across. Within that cluster, every galaxy is in motion. The dwarf galaxies orbit their parent giants. The 2 giants edge toward each other along a slow gravitational track. The motions are real, but the timescales are very long. The cluster as a whole is held together by gravity, and on the largest timescales, the galaxies are settling, slowly, into a single, combined gravitational system. The Milky Way and Andromeda are slowly approaching each other. The relative speed between them is roughly 110 kilometers per second along the line of sight, with smaller motions across the line of sight that astronomers have only recently been able to measure with high precision. The 2 galaxies are on a slow collision course, and on a timescale of several billion years, they will merge into a single larger elliptical galaxy. Long before they touch, their gravitational influence on each other will already have begun to reshape both disks. The Milky Way's motion within the local group is a separate component of the solar system's total motion through space. Even after subtracting the Sun's orbital motion around the galactic center, the entire galactic disk is drifting through the local group's gravitational well in a slow, shared orbit with Andromeda. The local group is not at rest in any frame larger than itself. It carries its own coherent motion through the larger universe. The dwarf galaxies of the local group orbit their parent giants in long loops, with their own peculiar velocities. The Magellanic Clouds, the 2 largest companions of the Milky Way, are bound to our galaxy on long orbits and contribute their own small share of motion. The Triangulum Galaxy, the third largest member of the local group, orbits within the larger shared well. From the outside, the local group looks like a slow waltz. Two large galaxies edging toward each other, surrounded by smaller galaxies looping through the shared gravitational field. That motion is very slow on human timescales. The Milky Way and Andromeda will not actually meet for several billion years, and the first close passage will not happen for nearly that long. But on galactic timescales, the motion is decisive. The collision between the two giant disks is one of the more certain events in the galaxy's long calendar. When the eventual collision unfolds, the two disks will not crash into each other in any sudden sense. The stars within each galaxy are so widely separated that direct stellar collisions are essentially impossible. The galaxies will pass through each other in slow motion, with the gravitational influence of each disk reshaping the other over the course of several 100 million years. The two disks will deform, throw out long tidal tails of stars and gas, and eventually settle into a combined, larger structure. The merged galaxy will not be a spiral anymore. The orderly disk structures will have been disrupted, and the merged remnant will likely settle into an elliptical galaxy with a much smoother stellar distribution. That is a very distant future event. From the present moment, the Andromeda Galaxy is visible from dark skies as a small fuzzy patch near the constellation Andromeda in the autumn sky from the northern hemisphere. The patch is the bright central bulge of the galaxy, with the rest of the disk too faint to see without a telescope. The light reaching the eye from that patch began its journey 2.5 million years ago and has been traveling through space ever since. The galaxy is the most distant object visible to the unaided eye from Earth, and it is the largest member of the local group apart from our own galaxy. When astronomers want to compute the motion of the solar system on the largest cosmic scales, it is often useful to step back from the individual motions inside the local group and consider the local group as a single unit moving through the larger universe. The cluster has its own center of mass, and that center has its own motion relative to the wider network of nearby galaxy clusters and superclusters. That motion is much larger than the motions inside the group. While the Milky Way and Andromeda approach each other at about 110 kilometers per second, the entire local group is moving at more than 600 kilometers per second relative to the average frame of the local universe, and at about 620 kilometers per second when measured against the cosmic microwave background. That is the largest coherent, organized motion in our local cosmic neighborhood, and it points in a direction that goes far beyond the boundary of the local group itself. That direction, and the larger structure that produces it, is the next layer in the nested motions. The composition of the local group is worth pausing on for a moment, because the Milky Way is not the only large galaxy in our local cluster, and the picture of the cluster has been refined considerably in recent decades. The Andromeda Galaxy, also called Messier 31, is the largest member of the local group by some measures, with a diameter roughly comparable to or slightly larger than the Milky Way. The two giants face each other across about 2.5 million light-years of space, and they are by far the most massive members of the cluster. The third largest galaxy, the Triangulum Galaxy, also called Messier 33, is a smaller spiral located near Andromeda, and it is sometimes considered a possible satellite of Andromeda rather than an independent member of the local group. The remaining members are mostly dwarf galaxies, small, irregular collections of stars and gas with masses ranging from a few million to a few billion times the mass of the Sun. The Magellanic Clouds, the large and small Magellanic Clouds, are the most prominent dwarf companions of the Milky Way, visible to the naked eye from southern latitudes and held in long, complex orbits around the larger disk. Around Andromeda, there are a similar collection of dwarf satellites, and there are also several isolated dwarf galaxies that do not appear to be bound to either giant, but drift independently through the local group's gravitational well. The total population of the cluster is at least 100 galaxies, with new, very faint dwarfs being discovered regularly as deeper surveys map the cluster's outer regions. All of these galaxies are in motion. The dwarfs orbit their parent giants. The giants edge toward each other. The independent dwarfs drift through the shared gravitational field. The motions are coherent on the largest scale, in the sense that they are all bound by the same gravitational system, but they are diverse in their specific directions and speeds. The cluster as a whole is the only object that has a single coherent motion through the larger universe. Inside the cluster, every member has its own peculiar velocity. There is something gentle about that picture. The galaxies of the local group are not arranged in any tidy pattern. They are simply a small collection of objects bound together by gravity, slowly orbiting each other on timescales of billions of years, drifting through the larger cosmic structure as a single dim glow against the deeper sky. From a vantage point a few million light-years away, the local group would appear as a small group of luminous structures, two large spirals and a collection of smaller smudges, all drifting together through the wider universe. The Milky Way is one of those two spirals. The body resting on the surface of the Earth is, in this picture, on a small rocky planet orbiting an ordinary star in the disk of one of those two spirals in a small cluster of galaxies that is itself drifting through the wider cosmic web at speeds far larger than anything inside the cluster. The frames keep nesting, and at each level the previous frame becomes a smaller and smaller piece of the larger picture. Part 6. The local group toward the great attractor. The local group is being pulled. Not toward Andromeda, which is an internal motion within the cluster, but in a coherent direction outside the group, toward a region of higher than average mass concentration in the larger cosmic structure. That region is called the Great Attractor, and the bulk motion of the local group toward it is one of the largest organized flows ever measured in the universe. The Great Attractor lies in the direction of the constellations Centaurus and Hydra in the southern sky. It is partly hidden behind the plane of our own galaxy, in a band of stars and gas so dense that for decades it concealed the structures behind it from optical telescopes. The region of sky where the disk of the Milky Way blocks the rest of the universe is called the zone of avoidance, and the Great Attractor sits squarely behind it. That hiding was significant for the history of the discovery. For a long time, astronomers studying the motion of the local group relative to the cosmic microwave background could measure a clear flow, but they could not point at the source of the flow with confidence, because the source lay behind the obscuring band of our own galaxy. Only with the advent of infrared and radio observations, which penetrate the dust of the disk in ways that visible light cannot, did the structures behind the zone of avoidance begin to come into view. When the structures came into view, they were not subtle. The Great Attractor turned out to be associated with a large concentration of galaxy clusters in the Hydra-Centaurus direction, with masses on the order of tens of thousands of times the mass of the local group combined. Behind it, the Shapley supercluster turned out to be even larger, with a total mass that may exceed the Great Attractor itself by another factor of several. The combined gravitational pull of these structures, together with the more distant network of the cosmic web extending in the same direction, is sufficient to draw the local group at 600 kilometers per second relative to the cosmic frame. The zone of avoidance still hides part of the picture. Even modern infrared and radio surveys cannot map the structures behind the most obscured central regions of the Milky Way with the same precision as the unobscured sky. There may be additional structures behind the zone that contribute to the pull, structures that have not yet been fully catalogued. The radio galaxy dipole, which counts sources across the entire sky, including through the zone, is one of the ways to look for such hidden contributions, because radio waves pass through dust more easily than any other wavelength of light. The local group as a whole moves at roughly 620 kilometers per second relative to the cosmic microwave background. That motion is not in any random direction. It is directed toward the Hydra and Centaurus region, the same general direction as the Great Attractor. The local group is, in a real sense, falling slowly toward a region of higher than average density in the cosmic web, drawn there by gravity over billions of years. That bulk flow is the largest single motion the solar system participates in within the nested cosmic frames. The Sun's orbital motion around the galactic center is much larger as an instantaneous speed, but it is a closed orbit that loops back on itself. The bulk flow toward the Great Attractor is a one-way trip, an inflow into the larger cosmic web, accumulated over the lifetime of the universe. In recent decades, astronomers have come to understand that the Great Attractor is itself part of a larger structure. Beyond the Great Attractor, in the same general direction, lies an even denser concentration of galaxies called the Shapley supercluster. The local group, the Virgo supercluster, the Hydra-Centaurus supercluster, and the Shapley supercluster are all parts of an enormous structure now called Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is the supercluster the Milky Way belongs to. Its gravitational center sits roughly in the direction of the Great Attractor. The bulk flow of the local group is, in essence, the flow within Laniakea, the slow gravitational settling of one local galaxy cluster into the wider supercluster to which it belongs. This is the third nesting of motion. The Earth orbits the Sun. The Sun orbits the galaxy. The galaxy orbits within the local group. The local group flows through Laniakea, drawn toward the Great Attractor and toward the larger Shapley concentration beyond. Each motion is real. Each one is independent of the others. Each one is added to the total motion of any point on the Earth through the universe. The motion does not feel like falling. From inside the frame, the local group is at rest. The galaxies inside it orbit each other in their slow patterns. The disks turn at their normal rates. The stars within the disks carry their normal peculiar velocities. The much larger motion of the whole cluster, sailing through the cosmic web toward the Great Attractor at 600 kilometers per second, is invisible to anything inside it. The same principle that hides the Earth's orbit from the body on the surface hides the local group's bulk flow from any galaxy embedded within it. The frame is moving as a whole. There is no reference inside the frame to feel the motion against. To feel that motion, one must look outside the frame. The cosmic microwave background, which fills the whole universe with the leftover light of its early stages, provides exactly that outside reference. There is a useful image for thinking about the bulk flow. The cosmic web, the largest known structure in the universe, is a vast network of long filaments of galaxies separated by enormous, nearly empty voids. The filaments are where the cosmic matter has gravitationally settled over billions of years. The voids are where it has thinned out. The web spans the entire observable universe, and every cluster of galaxies sits somewhere along its threads. The Milky Way and the local group sit at one of the intersections of the cosmic web in a region of moderate density. The Great Attractor sits at another, larger intersection in the direction of Hydra and Centaurus. The Shapley supercluster sits at an even larger one, farther in the same direction. The local universe is, In essence, a long thread of denser regions stretching from our position outward toward Shapley, with the local group falling slowly down that thread toward higher density. That falling is the bulk flow. It is not a sudden plunge or a rapid motion in any human sense. It is a slow gravitational settling, accumulated over the lifetime of the universe, expressed as a coherent velocity of 620 kilometers per second relative to the cosmic frame. The local group is one of many local clusters falling in this way, along various threads of the cosmic web. The same picture, on different scales, repeats throughout the observable universe. There is a soft logic to that motion. The universe is not in a state of equilibrium. It is still settling. The matter that condensed out of the early universe into galaxies, clusters, and superclusters is still gravitationally rearranging itself, drawing the denser regions closer together and emptying the voids more thoroughly. The bulk flow of the local group toward the great attractor is, in this larger view, part of a much wider gravitational arrangement that will continue for billions of years more. Of course, the expansion of the universe will eventually win out over most of these motions. The accelerating expansion of space, driven by what cosmologists call dark energy, will eventually push the great superclusters apart from each other faster than they can fall together. Long before the universe ends, the great attractor will recede from us. The Shapley supercluster will recede from us, and the local group will be effectively isolated in an expanding sea of intergalactic space. But that is a story for a much later time. For now, the bulk flow is the dominant large-scale motion of our region, and the local group is one of many small clusters falling slowly through the cosmic web. Part 7. The Solar System through the Cosmic Microwave Background. There is one more reference frame, and it is the largest one available. The cosmic microwave background is the oldest light in the universe. It was emitted at a time when the universe was much younger, much smaller, and much hotter than it is now. About 380,000 years after the universe began, the cosmos had cooled enough for free electrons to combine with atomic nuclei into neutral atoms. At that moment, the light that had been bouncing endlessly between charged particles was suddenly free to travel in straight lines. It has been traveling outward in all directions ever since, stretched and cooled by the expansion of space, until today it shines as a faint microwave glow, filling the entire sky. That glow is nearly perfectly uniform. The temperature of the cosmic microwave background is the same in every direction to within tiny fractions of a degree. But it is not exactly uniform. There is a small pattern superimposed on it called the dipole anisotropy, in which one hemisphere of the sky is very slightly warmer than the opposite hemisphere. That dipole is not a real difference in the temperature of the early universe. It is the signature of our own motion through the cosmic microwave background. The reason a moving observer sees a dipole in the cosmic microwave background is straightforward. Motion changes the apparent wavelength and intensity of light. Looking in the direction of motion, the photons of the background light appear slightly blue-shifted and slightly hotter. Looking in the opposite direction, the photons appear slightly red-shifted and slightly cooler. The cooler and warmer hemispheres are a kind of cosmic windshield. The side of the universe, the solar system, is moving toward looks warmer. The side it is moving away from looks cooler. The size of that temperature difference is very small, only a few thousandths of a degree above and below the average. But it is precisely measurable. From its size and direction, astronomers can recover both the speed and the direction of the solar system's motion. The total speed of the solar system relative to the cosmic microwave background derived from the dipole is about 370 kilometers per second. That is about 827,000 miles per hour. The direction of the motion, as recovered from the dipole, is toward the constellation Leo, near the boundary with the constellation Crater. That direction does not correspond to any of the smaller motions in the nested layers. It is not the direction of the Sun's orbit around the galaxy, which points toward Cygnus. It is not the direction of the Sun's drift through nearby stars, which points toward Hercules. It is not the direction of the Milky Way's motion within the local group, which points toward Andromeda. It is the resultant of all the motions added together, pointed toward a specific patch of the sky. Every night, the constellation Leo rises in the east. And every night, the solar system is moving at about 370 kilometers per second toward that constellation, relative to the oldest light in the universe. That is the closest thing to an absolute speed the solar system has. The cosmic microwave background is special in cosmology because it has no preferred direction of its own. The early universe was uniform. There were no large structures, no clumps of matter pulling in one direction and not another. The light from that era fills the sky evenly, and its rest frame is the rest frame of the average matter of the early universe. The discovery of the cosmic microwave background is one of the more accidental stories in the history of science. The microwave glow was first detected as an unexplained noise in a radio antenna built for entirely different purposes. The noise was uniform, faint, and persistent, regardless of where the antenna was pointed in the sky. After exhaustive efforts to eliminate it as a local source of interference, the researchers eventually realized that they were picking up a real signal from the universe itself, the predicted afterglow of the hot, early phase of cosmic history. That discovery became one of the foundational pieces of evidence for the standard model of cosmology, and it has been a continuous source of information about the early universe ever since. The dipole pattern in the cosmic microwave background was identified later as more precise measurements revealed that the temperature of the glow was not exactly uniform across the sky, but carried a slight bias along one direction. The interpretation as a sign of the solar system's motion was straightforward once the data were clear enough to see the pattern. Subsequent space missions refined the measurement, mapped the entire sky in microwave wavelengths with extraordinary precision, and produced the well-known figure of 370 kilometers per second toward Leo. That average frame is sometimes called the cosmic rest frame. It functions as the closest thing the universe has to a privileged frame of reference. It is not absolute in the sense that older physics imagined. There is no center, no preferred direction in space itself. But the cosmic rest frame is the frame against which the largest scale structure of the universe is most naturally measured. And it is the frame against which the solar system's motion can be expressed as a single coherent number, about 370 kilometers per second toward Leo. That number is the conventional answer to the question of how fast the solar system is moving through space. It is the result of decades of measurement, refined to high precision by dedicated space telescopes that map the cosmic microwave background across the whole sky. It is the number every textbook quotes when the question is asked. There is a moment of quiet reflection worth pausing on here. The cosmic microwave background was emitted at an age of the universe so early that no stars existed yet, no galaxies, no planets, no rocky bodies of any kind. The universe was a hot, dense, smooth fog of hydrogen and helium plasma with no structure of the kind we are familiar with today. The light from that fog has been streaming outward through the expanding universe for almost 14 billion years to reach us. The pattern of that light, smoothed by the long journey, is now the most uniform light source known. Across the entire sky, it shines at the same temperature to within tiny fractions of a degree, except for the small dipole pattern that encodes our own motion. That is a quietly remarkable arrangement. The oldest light in the universe carries within it a precise reading of our current motion, encoded in the small temperature difference between two halves of the sky. The light itself does not know about us. It was emitted long before we existed. But by passing through the expanding universe and being collected by our instruments at this particular moment in cosmic history, it offers a frame of reference against which our motion can be measured. The universe provides its own speedometer, and we have built the instruments capable of reading it. The dipole measurement has been refined over several decades by progressively more capable satellites. Each successive instrument has produced a more precise figure, and the basic result has remained stable. 370 kilometers per second toward Leo, plus or minus a small uncertainty. The number has not moved much. The direction has not moved much. The measurement has been treated, in the community of cosmologists, as one of the most solid quantities in the field. That number has just been put under serious pressure by a new measurement. Part 8. The new measurement, radio galaxies, and the headwind of motion. In recent years, a different technique has been developed for measuring the solar system's motion relative to the distant universe. Rather than reading the dipole in the cosmic microwave background directly, this technique counts the number of distant galaxies visible in different directions of the sky, looking for the same kind of asymmetry produced by motion. The logic is straightforward. If the solar system is moving in some direction, then for the same reasons the microwave background appears warmer in that direction, the distant galaxies in that direction should appear slightly brighter, slightly more numerous, and slightly bluer. Motion compresses the apparent flux of distant sources ahead of the observer and spreads it out behind. A careful count of galaxies across the sky should therefore show a small excess in the direction of motion, a kind of headwind of galaxies, with slightly more sources visible in the forward direction than in the rear. The analogy used in the recent study is helpful. Imagine driving a car through a steady rain. The rain is falling uniformly on all sides, but because the car is moving forward, more raindrops strike the windshield than the back window. If you wanted to measure how fast the car was going without looking at the road, you could count the raindrops on each surface and compute the difference. The greater the asymmetry, the faster the car is moving. The solar system moves through a universe filled with distant galaxies the way the car moves through rain. The galaxies are not falling, of course. They are simply distributed throughout the universe, with their light reaching the Earth from every direction. But the motion of the solar system compresses the apparent distribution in the forward direction and spreads it in the rear. The asymmetry is small, but it is measurable, and it gives an independent estimate of the solar system's speed and direction. The study that produced the new measurement focused on radio galaxies, galaxies that emit strong radio waves, often from active black holes at their centers driving enormous jets of plasma into intergalactic space. Radio waves have an advantage over visible light. They pass through the dust and gas of the Milky Way without being absorbed or scattered. Visible light from distant galaxies has to fight through the obscuring material of our own disk, especially in the direction of the galactic plane. Radio waves do not. They reach the Earth from any direction with very little local interference. That makes radio galaxies a clean sample. They can be counted in every direction of the sky, including through the plane of the Milky Way, where optical galaxy counts are heavily obscured. A radio survey can produce a uniform map of the distant universe across the entire sky, and the asymmetry between hemispheres in that map encodes the solar system's motion. The new measurement combined data from several radio observatories, including a vast network of antennas spread across Europe. The network is called the Low Frequency Array, often shortened to LOFAR, and it consists of thousands of antennas in stations across multiple countries, all linked together into a single virtual instrument. By combining the signals from all the stations, the network can produce extremely sensitive maps of the radio sky at low frequencies, sensitive enough to detect the small asymmetry expected from the solar system's motion. 2 additional radio observatories contributed data to the survey, giving a more complete sky coverage than any single instrument would provide. Together, the 3 datasets produced the first precise count of radio galaxies and their distribution across the sky, with the sensitivity needed to look for the small motion-induced dipole. The expected result was straightforward. The standard model of cosmology predicts that the solar system's motion through the distant universe should produce a small asymmetry in radio galaxy counts, and the size of that asymmetry should match the dipole already known from the cosmic microwave background. Both methods should give the same speed and direction, because both are measuring the same underlying motion of the solar system relative to the cosmic frame. Instead, the measurement found something else. The radio galaxy dipole was about 3.7 times larger than the standard model predicts. The direction matched the cosmic microwave background dipole within the measurement's accuracy. But the strength of the asymmetry was far greater than expected. Read literally, that result would imply that the solar system is moving more than 3 times faster than the established figure of 370 kilometers per second. That would be an extraordinary number. It would mean a motion of more than 1,000 kilometers per second relative to the average frame of the local universe, a motion no other measurement has detected and no current theoretical framework predicts. The statistical significance of the result was more than 5 sigma, which in physics is the conventional threshold for treating a result as not a fluke. Something real has been measured. The question is what? For now, the answer is uncertain. The result has been published in a peer-reviewed journal. It has been examined by independent teams of astronomers. It has not been explained away as a calibration error or a software bug. The data appear to be telling us that either the solar system is moving much faster than we thought, or the universe is less uniform on large scales than the standard model assumes, or both, or some combination of factors not yet fully understood. A few additional details about the measurement help to ground the picture. The low-frequency array is one of the largest radio astronomy projects ever built, with antennas distributed across multiple European countries and combined into a single virtual telescope through careful synchronization of the signals from each station. The total number of antennas runs into the tens of thousands, with the largest stations in the host country and smaller stations in partner countries that contribute to the longest baselines, the long distances between stations that give the array its sharpest angular resolution. By combining the signals from all the stations, the array can effectively act as a single radio telescope with a diameter spanning much of the European continent. That diameter sets the resolution. The array can distinguish between sources separated by very small angles on the sky, and it can do so across the entire visible hemisphere at any given time. The combined map of the radio sky produced by such an array is far more detailed than any earlier radio survey, with millions of distant sources catalogued at low frequencies that pass cleanly through the dust of the Milky Way. The 2 additional radio observatories that contributed to the new measurement provide complementary sky coverage. One operates from the Indian subcontinent, the other from the southern hemisphere. Together, the 3 datasets cover essentially the entire sky at the radio frequencies of interest, which is essential for measuring a dipole, because a dipole is a comparison between two opposite hemispheres of the sky. Any survey that covers only one hemisphere cannot, by itself, determine the dipole. Only by combining surveys from observatories in different parts of the world can the full sky be assembled into a single map. The analysis of the assembled map then involves counting the radio galaxies in different directions and looking for the small asymmetry that motion would produce. The analysis must account for the small differences in sensitivity between the contributing observatories, for the effects of the Milky Way's own radio emission contaminating parts of the sky, for the angular distribution of the surveyed galaxies, and for many other subtle effects that could mimic or hide the signal of interest. Modern statistical techniques and careful calibration are required to separate the motion signal from the noise. The result that emerged from that analysis is the dipole that came in 3.7 times stronger than expected. The statistical confidence is high. The direction matches the cosmic microwave background dipole within the precision of the measurement. The magnitude is far larger. And that is the situation the cosmological community is now sitting with. Part 9. What the discrepancy could mean. The radio galaxy dipole and the cosmic microwave background dipole should, in principle, give the same answer. They are two different ways of measuring the same motion of the solar system through the cosmic frame. When they disagree, one of three broad explanations is usually considered. The first possibility is that the universe is less uniform than the Standard Model assumes. The Standard Model of cosmology rests on the principle that, on large enough scales, the universe is statistically the same in every direction. Galaxies are distributed in a vast cosmic web, but when averaged over large enough patches of sky, the average density of galaxies in any direction should be the same as in any other direction. That assumption is called the cosmological principle, and it is one of the foundation stones of modern cosmology. If the cosmological principle holds, the dipole in the radio galaxy counts must be entirely due to our motion, and the discrepancy with the cosmic microwave background dipole becomes a puzzle. But if the cosmological principle does not hold perfectly, if there is some residual large-scale unevenness in the distribution of radio galaxies that is not due to our motion, then the dipole could be partly an intrinsic property of the universe, rather than entirely an effect of our motion. In that case, the solar system might still be moving at the speed the cosmic microwave background dipole suggests, but the radio sky would have its own additional asymmetry layered on top of the motion signal. That possibility would be a major result in its own right. The cosmological principle is a foundational assumption used in nearly every calculation of cosmic structure, expansion, and evolution. A confirmed violation of the principle on the scales probed by the radio survey would force a rethinking of how the universe's large-scale structure formed and arranged itself. The second possibility is to take the result at face value. The radio galaxy dipole is what it appears to be, a motion-induced asymmetry caused entirely by the solar system's motion through the cosmic frame. In that case, the solar system is moving at more than 3 times the speed previously attributed to it, and the cosmic microwave background dipole is somehow underestimating the true motion. That interpretation has its own difficulties. The cosmic microwave background dipole is one of the most precisely measured quantities in all of cosmology, and the techniques used to extract it have been refined over decades. It is not easy to argue that the dipole has been systematically underestimated by such a large factor. And if the solar system really is moving at over 1,000 kilometers per second relative to the cosmic frame, the gravitational source of that motion must be identified. Such a large bulk flow would imply a much larger nearby concentration of mass than current cosmic structure maps reveal, a hidden gravitational source pulling our entire region of the universe toward it at a speed far exceeding anything previously imagined. Some astronomers have suggested that such a hidden gravitational source might exist, either in the form of a much larger, Shapley-like supercluster beyond what has been mapped, or in the form of a previously unmeasured large-scale void in some other direction, effectively pushing our region of the universe in the direction of measured motion. None of those candidates is currently supported by independent evidence at the required strength. The third possibility is more subtle. The cosmic microwave background dipole measures the solar system's motion relative to the average frame of the early universe, the frame defined by the matter that emitted the background light almost 14 billion years ago, when the universe was only 380,000 years old. The radio galaxy dipole measures the solar system's motion relative to the distribution of galaxies as they exist now, averaged over the recent universe, with galaxies that emitted their light over a range of times in the past few billion years. If the universe were perfectly homogeneous and isotropic on all scales, those two frames would coincide exactly. But if the local universe has some net motion relative to the early universe frame, a bulk flow extending out to vast scales, then the radio galaxy frame and the cosmic microwave background frame are not the same. The solar system would have one motion relative to the early universe frame and a different motion relative to the local universe frame, and the discrepancy between the two measurements would be a real physical effect. Bulk flows of that kind have been hinted at in other surveys, though never with such strong statistical significance as in the radio galaxy measurement. A confirmed bulk flow on the scale required by the radio dipole would imply structure in the universe on scales larger than the standard model of cosmology comfortably allows, a kind of organized motion of vast regions of space that would, like the violation of the cosmological principle, require a substantial rethinking of large-scale structure formation. The three possibilities are not mutually exclusive. A combination of mild violations of the cosmological principle, a real bulk flow, and improved measurement of both dipoles could resolve the discrepancy with no single dramatic conclusion. But all three possibilities point in the same direction. The universe's largest scale motions are less settled than the standard picture suggests, and a long-standing question, how fast are we moving through space, and against what, has been reopened. It is worth dwelling on what a real bulk flow on the required scale would mean in physical terms. A bulk flow is a coherent motion of a vast region of the universe relative to the average frame defined by the cosmic microwave background. If our region of the universe is participating in such a flow, then everything within that region, every galaxy, every cluster, every supercluster, within the volume of the flow, is moving in roughly the same direction, with roughly the same speed. The local group, the Virgo supercluster, and a large portion of the surrounding cosmic web would all be sailing together through the larger cosmic frame, drawn by some imbalance of mass distribution outside the volume. That kind of coherent, large-scale motion is allowed in principle by the standard model, but only on relatively small scales and at relatively small speeds. As the scale of the volume grows larger, the predicted bulk flow speed shrinks, because the universe should be more uniform when averaged over larger volumes. A large bulk flow on a very large scale would be in tension with that prediction. The discrepancy between the radio galaxy dipole and the cosmic microwave background dipole, if interpreted as a bulk flow, would imply a flow on a scale and at a speed that the standard model does not comfortably permit. There are also subtler interpretations involving the calibration of the radio survey itself. The radio galaxies counted in the survey are not all at the same distance. They span a wide range of redshifts, from relatively nearby galaxies whose light has traveled for a small fraction of cosmic history, to extremely distant galaxies whose light has been traveling for much of the age of the universe. The dipole measured from the count is, in some sense, an averaged dipole over the entire range of distances. If the bulk flow varies with distance, the average signal might be different from the signal that would be measured from any single redshift slice. Resolving the dipole as a function of distance is one of the key directions of follow-up work, and it requires more sophisticated analysis than a simple skywide count. For now, the result stands as it was reported. The dipole is 3.7 times stronger than the standard model predicts. The cause is not yet established. The cosmological community will continue to work on the question for years to come. The universe, meanwhile, will continue to move in whatever way it actually moves, regardless of how quickly we understand it. The result will be tested. Astronomers are already designing new surveys with greater sensitivity, broader sky coverage, and better control of systematic errors. The next generation of radio observatories will be able to repeat the measurement with even more distant galaxies and even sharper precision. If the result holds up, it will be one of the most important measurements of the decade. If it does not, the analysis will sharpen the methods used to extract such delicate signals from the noise of the sky. Either way, the question has been put back into circulation. There is a quieter point worth holding here. Cosmology has had a slow accumulation of small puzzles over the past decade. The measured rate of expansion of the universe, derived from the cosmic microwave background and from observations of nearby supernovae, has produced different numbers depending on which method is used, and the difference has not gone away as the measurements have been refined. The growth of cosmic structure, measured from gravitational lensing and from galaxy clustering, has produced numbers that disagree slightly with the predictions of the standard model. The cosmic microwave background itself contains some statistical features that are slightly more extreme than the standard model would predict by chance. None of these puzzles is large on its own. None of them is so significant that any single one would force a major revision to the standard picture. But each of them is a small note of strain. Each is an indication that the standard model, which has been astonishingly successful at describing the broad behavior of the universe, may be missing something subtle. The new dipole measurement, with its 3.7 factor over the predicted value, is the largest of these notes of strain. It may end up being explained within the standard model. It may end up being the first clear evidence that the standard model needs to be extended. For the body lying down to sleep tonight, the resolution of those puzzles does not matter. The motion is happening, whatever it is. The frame is moving, whatever the precise number turns out to be. The body is being carried, whatever astronomers eventually conclude about the larger picture. The quiet at the center of it remains the quiet. Part 10. Adding the layers together. To get a sense of how fast the Earth is actually moving through space at any given moment, the layers of motion have to be combined. The simple way to do it is to add the motions vectorially, taking each one as a velocity with a direction and adding them tip to tail like arrows pointing through space. The Earth moves at about 30 kilometers per second around the Sun. The Sun moves at about 13 kilometers per second through the local stellar neighborhood in the direction of Hercules. The Sun also moves at about 220 kilometers per second around the galactic center in the direction of Cygnus. The Milky Way moves at about 110 kilometers per second toward Andromeda within the local group. The local group moves at about 620 kilometers per second toward Hydra and Centaurus relative to the cosmic microwave background. When all of those are combined, the Earth's total motion relative to the cosmic microwave background averages out to about 370 kilometers per second in the direction of Leo. That is the conventional answer to the question that opens this video. derived from the cosmic microwave background dipole and the kinematics of the local galactic neighborhood. It is the textbook number. 370 kilometers per second is more than 800,000 miles per hour. It is more than 1,000 times faster than the fastest commercial airliner. It is more than 10 times faster than any human-built spacecraft has ever traveled. It is the speed at which the Earth, and everyone on it, is sailing through the universe at this moment, toward the constellation Leo, relative to the oldest light there is. If the new radio galaxy measurement is taken at face value, that number rises to more than 1,000 kilometers per second, more than 2 million miles per hour, a speed at which the entire distance from the Earth to the Moon could be covered in about 120 seconds. A speed at which the entire diameter of the Earth could be crossed in about 13 seconds. A speed for which no part of the body has any way to feel anything at all. The direction the Earth is currently moving through the cosmic microwave background, toward Leo, is a direction that has no special meaning in the constellations themselves. Leo is a region of relatively quiet sky, containing a handful of bright stars and some distant galaxies, all of them moving with their own peculiar velocities through their own local frames. The direction is set by the vector sum of all the motions described above, and would shift slightly over very long timescales as those motions change. The motion is not toward anything in particular. There is nothing in Leo pulling the solar system in. The direction is simply the resultant of the slow gravitational settling of our region into the larger cosmic web, dominated by the pull of Hydra and Centaurus, and the Great Attractor and Laniakea beyond. The label, toward Leo, is a present tense address. It is not a destination. The constellation Leo is one of the older recognized patterns in the sky, a roughly lion-shaped grouping of stars visible from the northern hemisphere in the spring months. Its brightest star, Regulus, lies near the ecliptic plane and is one of the first magnitude stars of the sky. The other stars of the constellation form the curve of the lion's mane and the long body stretching out across the spring sky. None of those stars has anything physically to do with the solar system's motion toward Leo. They are scattered at distances of tens to hundreds of light years from the Sun, with their own peculiar motions and their own orbits around the galactic center. They simply happen to lie in the direction toward which the resultant of all the layered motions points. That is a useful thing to keep in mind. The direction of cosmic motion is a vector quantity, with no physical significance to whatever happens to lie in that direction on the sky. The constellations are accidents of human pattern recognition projected onto the dome of the sky. The motion is a physical reality projected through the same dome. Where they intersect is a happenstance of perspective. If the body of the Earth were translated to a different position in the galaxy, the same physical motion would point toward a different patch of sky entirely, picked out by whatever constellations happen to be in that direction from the new vantage. The vector is real. The label is local. It is worth pausing on the scale of this. 370 kilometers per second is the speed the solar system carries through the cosmic frame at this moment. That speed has been roughly constant on human timescales. It has been roughly constant on geological timescales. It has been roughly constant for most of the lifetime of the solar system. The Earth has been sailing through the universe at that speed for 4.5 billion years. Every dinosaur that ever walked the surface was moving at 370 kilometers per second toward Leo. Every star that ever rose was rising over a planet already in flight. Every footstep that has ever been taken on this surface was, at the same time, a footstep on a vehicle in motion at far greater speeds than any rocket has ever achieved. And none of it has ever been felt. The body, the room, The planet, the sun, the galaxy, the cluster, the supercluster, all of them carry the same motion, all of them move together, all of them register exactly nothing. The new radio galaxy measurement raises the possibility that the figure is much larger. If the Earth is moving at over 1,000 kilometers per second through the cosmic frame, the speed has been that way for a long time as well. There is no instant in the lifetime of any creature on this planet when the motion was different. The body has never known a slower frame. The new measurement, if taken at face value, simply updates the number we attach to a situation that has been quietly true the entire time. It is also worth describing how the layers compose to give the final number. Vector addition is the mathematical operation that combines two velocities into one. If one velocity points one way and another velocity points another way, their sum points in a direction somewhere between the two, with a magnitude that depends on the angle between them. When two velocities point in nearly the same direction, the sum is large. When they point in nearly opposite directions, the sum is small. When they point at right angles, the sum lies along the diagonal. The Earth's orbital velocity around the Sun, 30 kilometers per second, points in a direction that changes through the year as the Earth circles the Sun. At any given moment, the orbital velocity points along the orbital track at that moment, perpendicular to the line from the Earth to the Sun. The Sun's peculiar velocity, 13 kilometers per second toward Hercules, is roughly constant on the timescale of a human life. The galactic orbital velocity, 220 kilometers per second toward Cygnus, is also roughly constant on that timescale. The local group's bulk flow, 620 kilometers per second toward Hydra and Centaurus, is constant on even longer timescales. When all of these are added together as vectors, the result is the motion of the Earth through the cosmic frame. The arithmetic is not simple because the directions are different. Hercules, Cygnus, Andromeda, and Hydra are all in different parts of the sky, separated by angles of tens or hundreds of degrees. The vector sum involves projecting each motion onto common axes, adding the components, and recovering the magnitude and direction of the total. The result of that arithmetic is 370 kilometers per second toward Leo. That is the conventional answer. The radio galaxy measurement, if interpreted as a Doppler signal alone, would replace that with a much larger number, more than 1,000 kilometers per second, in the same general direction. Either way, the underlying motion is real, the direction is well defined, and the body lying down on the surface of the Earth is, in this very moment, being carried along it. There is also a humbling note in the arithmetic. The Earth's orbital speed, large as it feels in everyday terms, contributes only a small fraction of the total motion through the cosmic frame. The orbital speed adds or subtracts about 30 kilometers per second from the total, depending on the time of year and the orientation of the orbit. That is less than a tenth of the cosmic microwave background dipole value, and a much smaller fraction of the radio galaxy dipole value. The dominant motions are the galactic and intergalactic ones, with the Earth's own orbit and the Sun's peculiar velocity contributing relatively modest corrections on top. The body is not, in this picture, primarily a passenger of the Earth around the Sun. The body is primarily a passenger of the Milky Way, around the local group, of the local group within Laniakea, and of Laniakea within the wider cosmic frame. One guise, those are the dominant currents. The Earth's orbit is the smallest current the body rides, but it is also the most directly observable one, the one whose pattern the species has known about for the longest period of its history. The larger currents have been mapped only in the past century, and the largest of them is being remeasured even now. Part 11. Why the motion cannot be felt. The body lying down to sleep tonight is being carried at more than 800,000 miles an hour through the universe. It is rotating with the Earth at 1,000 miles an hour. It is orbiting the Sun at 67,000 miles an hour. It is sweeping along the galactic disk at 500,000 miles an hour. It is drifting through the local group, falling toward the Great Attractor, being carried with the Milky Way along the great current of Laniakea, all at the same time. And it feels like nothing at all. The reason for that is the same reason a passenger on a smoothly flying aeroplane does not feel the plane's motion. The body is in the frame. The atmosphere is in the frame. The Earth is in the frame. There is no part of the immediate environment that is not also moving at the same speed and in the same direction. There is no force the body can register as motion. There is only the steady stillness of being inside a frame that is moving as a whole. This is one of the basic results of physics. Motion at constant velocity is undetectable from inside a moving frame. The body can only register accelerations, changes in velocity. The push of a car when it speeds up, the tug of a turn, the lift of an elevator beginning to rise. None of the great motions of the solar system produce sustained acceleration that the body can detect. The Earth's orbit produces a tiny acceleration, the centripetal pull that keeps the planet curving around the Sun. That acceleration is far too small to be felt against the much larger pull of Earth's own gravity. The galactic orbit produces an even tinier centripetal acceleration. The motions through the local group, the bulk flow toward Hydra and Centaurus, the motion through the cosmic microwave background, all of them are essentially constant on any human timescale, and constant motion is silent to the body. That silence is one of the strangest gifts of physics. It is what allows a person to lie down at night and not feel the universe rushing past. The cosmos is moving at extraordinary speed around the body, and the body's frame is moving with it, and the body and the frame together register exactly nothing. The only motion that is felt is the small ones. The rise of the chest with the breath, the slow shift of a limb, the heartbeat. The big ones are all swallowed by the stillness of the shared frame. Because the motion cannot be felt, it has to be inferred. Every quantity in this video, the orbital speed of the Earth, the orbital speed of the Sun, the peculiar velocity through local stars, the bulk flow of the local group, the cosmic microwave background dipole, the radio galaxy dipole, is a measurement made by looking outside the local frame. By tracking the position of distant stars across the year, the Earth's orbital motion can be measured. By tracking the slight back and forth wobble of nearby stars caused by the Sun's gravity, the Sun's peculiar velocity can be measured. By measuring the temperature pattern of the cosmic background, the motion through the cosmic frame can be measured. By counting distant radio galaxies in different directions of the sky, the motion can be measured a different way again. Each of those measurements is, in a sense, a borrowed sense, a way of feeling something the body has no nerve for. The instruments stand in for nerves the body never grew. The dipole in the cosmic microwave background is the universe's way of telling the body how fast it is moving. The body cannot read it directly, but astronomers can build instruments that can. And the instruments report more than 800,000 miles an hour toward Leo, relative to the oldest light there is. Possibly more, depending on which dipole is trusted. It is worth holding that thought for a moment. The body is not a passenger in some dimly understood vehicle, ignorant of where it is going. The body is a passenger in a vehicle that has been measured. The speed has been clocked. The direction has been read. The fact that the body cannot feel the motion does not mean the motion is hidden. It means only that the body and the instruments report different things because they have different access to the world. The instruments see the larger frame. The body sees only itself. In that asymmetry, the body comes out ahead in one specific way. The instruments report motion. The body reports stillness. Both are correct in their own frame. The body is allowed to rest. The instruments are allowed to measure. And the universe is allowed to keep moving at its own enormous speeds around all of it without ever asking anyone inside the frame to notice. The principle that motion at constant velocity cannot be felt is sometimes called the principle of relativity, and it has been one of the foundational ideas of modern physics for several centuries. The idea is sometimes traced back to Galileo, who pointed out that a passenger inside a smoothly moving ship below decks would have no way to tell from inside the cabin whether the ship was moving or sitting at the dock. Any experiment conducted entirely within the cabin would give the same result either way. The motion of the ship, however large, is invisible to any observation made entirely inside the ship. That principle extends directly to the Earth's motion through the universe. The Earth is a ship. The body is a passenger inside the cabin of that ship. Any experiment conducted entirely on the surface of the Earth gives results consistent with the Earth being at rest. The only way to detect the motion is to look outside the ship, at the distant stars, at the cosmic microwave background, at the distant radio galaxies. The principle of relativity is the reason the motion cannot be felt. It is also the reason the motion can be measured by looking at the relative position and shift of things outside the local frame. The principle, extended further by later physicists, also tells us something subtle about reference frames. There is no absolute frame of rest in the universe. There is no special vantage point from which all motion can be measured. Every frame is equally valid for doing physics. The cosmic microwave background provides a natural frame because of its uniformity, but it is not a privileged frame in the sense of being the true rest frame of the universe. It is simply the frame in which the average matter of the early universe was at rest, and against which the motions of all later matter can be most naturally compared. That gentle democracy of frames is one of the quieter beauties of physics. The Earth has its frame. The Sun has its frame. The galaxy has its frame. The cosmic microwave background has its frame. None of them is more fundamental than any other. All of them are simply different ways of organizing the same underlying motion. The body inside the Earth's frame is correctly reporting its rest. The instruments measuring the cosmic microwave background dipole are correctly reporting the motion. Both descriptions are true at the same time. They simply belong to different frames. This is the soft physics of being carried. The body is carried by a frame. The frame is carried by another frame. The other frame is carried by yet another, all the way out to the largest frame the universe provides. Each carrying is real. None of them is felt. The body rests at the center of it all, in the small frame it is allowed to inhabit, while the larger frames do all of the larger work. Part 12. A brief history of the question. The question of how fast the Earth is moving has been asked in different forms for centuries. The earliest astronomers assumed that the Earth did not move at all. The heavens were thought to turn around a fixed Earth, with the stars carried on a great rotating sphere, the planets carried on inner spheres of their own, and the sun and moon moving along their own celestial tracks. The Earth itself was the still center, and the visible motion of the sky was the motion of the heavens around it. That picture was natural. The Earth feels still. The sky visibly turns. The patterns of the planets follow elegant, slow patterns. The model worked, in a rough sense, for many centuries. It allowed for prediction of eclipses, the rough motion of the sun through the year, the rising and setting of stars at the same times. It was the picture every ancient civilization could see when it looked up. The eventual reversal of that picture, the recognition that the Earth orbits the Sun and that the Sun is one of many stars, produced the first real answer to the question of how fast the Earth is moving. Once it was understood that the Earth's apparent stillness was an illusion produced by being inside a moving frame, the orbital speed could be calculated from the size of the orbit and the length of the year. The answer turned out to be a number much larger than human experience could prepare for. 30 kilometers per second, 67,000 miles per hour. An invisible motion of the ground itself, carrying every living thing on its surface. Each subsequent recognition added another layer. The sun is not still. It moves through the local stars. The local stars are not still. They orbit the galactic center. The galaxy is not still. It moves within the local group. The local group is not still. It flows toward the great attractor. And the largest discovery in this thread, in the 20th century, was that none of them are still relative to a frame the universe itself provides. The cosmic microwave background sets a kind of universal speedometer against which everything else can be measured. That progression took several centuries, and it was not always smooth. Each layer required new techniques, new instruments, and new arguments. The recognition of the sun's motion through the local neighborhood required precise measurements of stellar positions over long timescales. The recognition of the galactic orbital motion required the recognition that the Milky Way is a rotating disk of stars rather than a fixed background. The recognition of the local group's bulk flow required the discovery of the great attractor and the larger structures around it. The recognition of the cosmic microwave background dipole required the launch of dedicated space telescopes capable of measuring temperature differences of a few thousandths of a degree across the whole sky. Every one of those steps shifted the answer to the question. Every one of them was treated, at the time, as the final word. And every one of them was eventually layered with another, larger frame in which the previous answer was only a piece of the total. The new measurement, the radio galaxy dipole, that comes in more than 3 times stronger than expected, is the most recent step in that long climb outward. It is the first hint that the answer to the simple question may need to be revised yet again. Whether the revision is in the speed itself, in the assumed homogeneity of the universe, or in the relationship between the early universe frame and the recent universe frame, the question of how fast the solar system is moving has been reopened in a way it has not been for decades. That is, in a sense, the proper state for the question to be in. Every previous answer was provisional. Every previous answer was the best understanding at the time. The current best answer is provisional too. The radio galaxy measurement is the universe's gentle reminder that the largest motions in the cosmos are still being worked out, that the patient work of measuring how fast we are moving is not yet finished, and that the next decade will bring more data, more analysis, and more refinement. There is a quiet pattern in the history of these questions. Every time the question of how fast we are moving has been asked, the answer has turned out to be larger than expected. The early astronomers expected 0. The first heliocentric models produced 30 kilometers per second. The first galactic models added 220 more. The first cosmic microwave background measurements added another 70 or so on top. And now the radio galaxy measurement, if it stands, suggests that the total may be larger still, by another factor of more than 3. Each new layer has added speed to the answer, never subtracted it. There is no obvious reason for that pattern to continue, but it has been the pattern so far. The universe, every time it is asked, seems to confirm that the Earth is moving even faster than the most recent estimate. And in every case, the new motion has been silent. The body has never felt the difference. The room has never tilted. The lamp has never swayed. The motion is simply added to the inventory of things that are true but invisible, things that the instruments can read but the body cannot. The latest possible addition, 3 times faster than the cosmic microwave background dipole, would be no more felt than any of the others. The history of these discoveries has also been a history of slow patience. The recognition of the Earth's orbit took centuries to develop, with careful naked-eye observations of planetary positions gradually accumulating into a coherent model. The measurement of stellar parallax, the direct confirmation that the Earth orbits the Sun by means of the small annual shift in nearby stars, was first achieved by careful telescopic observations conducted over years of repeated measurements. The measurement of the Sun's motion through the local neighborhood required tracking the proper motions of thousands of nearby stars over decades, building up a statistical picture of how the local stellar field appears to be drifting from the Sun's vantage. None of these measurements happened quickly. None of them happened on the timescale of a single career, in most cases. The measurement of the galactic rotation curve and the realization that the outer disk rotates too fast for the visible mass alone to account for required the development of radio astronomy and the careful mapping of neutral hydrogen gas throughout the galactic disk. That work took decades. The discovery of the Great Attractor required the careful mapping of galaxy redshifts and peculiar velocities across large patches of sky, a project that began in the 1970s and continued through several generations of surveys. The cosmic microwave background dipole was first detected in the late 1960s and refined progressively by satellite missions across the following 4 decades. The pattern is that each layer of motion has taken time to measure, and time to interpret, and time to integrate into the larger picture. The new radio galaxy dipole is the most recent in that long sequence. Its full meaning will not be known for years, and possibly for decades. The next generation of radio telescopes will continue the work. The next refinement of the cosmic microwave background measurements will compare against it. The next surveys of distant galaxies will provide independent checks. And gradually, over the slow accumulation of years and decades, the picture will sharpen. That patience is one of the comforts of the work. There is no rush. The motions are happening on timescales of billions of years. The body has billions of years before it ever needs to worry about the next major reshuffling of the local universe. The work of figuring out how fast the solar system is moving is, in the deep view, a leisurely project. There is no urgency in it. Each measurement takes time. Each interpretation takes patience. And the night sky is willing to wait while the work continues. Part 13. The still body inside the moving frame. The video closes by coming back to where it began. The Earth feels still. The body feels still. The room is quiet. The bed is steady. And underneath that stillness, the Earth is moving at 30 kilometers per second around the Sun. The Sun is moving at 220 kilometers per second around the galaxy. The galaxy is moving at 600 kilometers per second through the local group's larger flow, and the whole structure is moving at 370 kilometers per second, possibly much more, through the cosmic microwave background toward the quiet constellation Leo. None of that is felt. None of it has to be felt. The frame is doing the carrying. The body is doing the resting. The universe is doing the moving. There is a kind of constant belief in that arrangement. The body is not asked to participate in any of the great motions. It is only asked to be present in the frame. The frame handles the rest. The orbits, the rotations, the bulk flows, the cosmic settling into the wider web, all of it is happening to the body, whether the body attends to it or not. The body's job, for the duration of this night, is only to rest. The instruments will keep measuring. The next radio survey will refine the dipole. The next generation of space telescopes will refine the cosmic microwave background measurement. The next astronomers will work out whether the discrepancy is real and what it means and how it fits into the larger picture. The slow climb outward will continue, with new layers added as they are discovered and new motions described as they are measured. But none of that will require anything of the body lying down to sleep tonight. The body will keep moving at over 800,000 miles per hour, possibly much more, in a direction toward a soft constellation on the eastern horizon. It will keep moving whether anyone notices or not. It will keep moving whether the new measurement holds up or is overturned. It will keep moving because the frame keeps moving, and the body is in the frame, and the frame is in another, larger frame, all the way out to the farthest measurable scale of the universe. The constellation Leo will rise in the east tonight, somewhere, depending on the season and the latitude. Somewhere, every night, it is rising for someone. And somewhere, every night, the Earth is moving toward it at speeds the body will never be able to feel. The motion is not destined for anywhere in particular. It is simply the slow gravitational settling of our region into the larger cosmic web, expressed as a direction in the sky. The Sun has been doing this for 4.5 billion years. The Milky Way has been doing this for much longer. The local group has been settling toward the Great Attractor for most of the history of the universe. The motion is older than the planet, older than the Sun, older than the galaxy itself. The body has only existed inside it for a moment, in the long sense of things, and during that moment, the body has not been asked to notice. It is not a small thing to be carried by a universe in motion. It is not a small thing for that motion to be silent. It is not a small thing for the body to be allowed to rest while the largest currents the cosmos makes available carry it through the night. There is something deeply old in the arrangement, something that predates everything human about the planet. The motion is older than the species. It is older than the family of mammals. It is older than the existence of bones, of nerves, of any cell that could ever have begun to feel anything. The motion has been continuous through all of that history. It will continue long after every individual member of the species has gone, and long after the species itself has changed beyond recognition. The motion is one of the steady backgrounds against which life has happened, and it will be one of the steady backgrounds against which whatever comes next will happen. The Sun will eventually grow into a red giant, several billion years from now, and the inner planets will be reshaped by that expansion. The Milky Way will eventually merge with Andromeda on a similar timescale, and the combined galaxy will settle into a larger elliptical shape with a different internal structure. The local group will continue its slow flow toward the Great Attractor, and on the largest timescales, the accelerating expansion of the universe will eventually carry the Great Attractor and Shapley out of reach. But all of these are far future events, beyond the horizon of any night that anyone alive now will ever spend on the surface of this planet. There is a long calmness in that arrangement. The future of the motion is not the concern of any individual night. The body does not need to know what comes next. The body does not need to predict the resolution of the dipole discrepancy. The body does not need to anticipate the merger with Andromeda. The body does not need to imagine the eventual recession of the great attractor. The body needs only to rest, while the motion happens around it and through it, the way it always has. For tonight, the situation is exactly what it has been for the entire lifetime of the solar system. The Earth orbits the Sun at 30 kilometers per second. The Sun orbits the galactic center at 220 kilometers per second. The galaxy moves within the local group. The local group flows toward the great attractor. The whole structure sails at 370 kilometers per second, possibly more, toward the soft constellation Leo, relative to the oldest light there is. The body is on the surface of the Earth, inside that whole assembly of motions, registering none of them. The room is steady. The bed does not shift. The lamp does not sway. Outside the window, the trees stand where they stood yesterday. Inside the window, the body rests. And underneath it all, the universe carries on doing what it has always done, at speeds the body will never have to feel. The instruments will continue their measurements. The next generation of radio telescopes will refine the dipole. The next generation of space telescopes will refine the cosmic microwave background measurement. The astronomers will continue to argue about whether the 3.7 factor is a real effect, a methodological artifact, or some combination of the two. The conversations will continue, the analyses will accumulate, and eventually, the question will resolve itself one way or another. But none of that resolution is required tonight. Tonight, the only thing required of the body is rest. The frame is doing the carrying. The room is steady. The breath is slow. The room will keep being steady. The breath will keep being slow. The Earth will keep orbiting the Sun will keep orbiting the galaxy, and the galaxy will keep being carried through the larger cosmic web, all without any input from the body lying on the surface of this small, ordinary, moving planet. And so we let the Earth keep moving the way it has always moved. Quietly, evenly, faster than anything the body could ever feel, toward a soft point in the sky we will never reach. The frame is doing the carrying. The night is doing the holding. The room is steady, the breath is slow, and the universe is doing what it has always done, around us and through us, without ever asking us to feel it. Let your breathing slow. Let your shoulders soften. Let the room grow steady around you. The frame is doing the carrying. The motion is happening the way it has always happened, around you and beneath you and beyond you, asking nothing of you in return. Rest now. The universe is awake on your behalf. Sleep well, and good night.